Okay, let's start again with the next talk. So the next talk is by Tim. Tim was a C++ developer. I don't know if you're still doing C++ a little bit, but
not a lot.
Made a few games, right? So in C++, but now he's working on Rust on the Pixie package manager at prefix.dev. And he's going to tell us all about the SAT solver used in Pixie. So give it a hand for Tim.
Okay, let's do this. I need to click. Oh, let me just check out this. Maybe I'll stand like this. Oh, it's a bit delay in this thing. Okay, let me just use the buttons then. So yeah, first off, who am I? I'm Tim. I work at prefix.dev. Yeah, thank you all for being here. It's great. I really like doing this. I was really excited that my talk got accepted. So I used to work on Reus, which was a game we made in C# basically, and then so that was fun. But we later on switched to C++ and Lua. After that, I worked in robotics in C++ and Python mostly, but we were already looking at Rust at that time, and I thought it was pretty awesome. I was already looking at Rust like in the 1.0 days, pre 1.0 days, sorry. And I thought it would look pretty cool, but we couldn't use it for games yet, so I never got around to using it. And then at our previous company, we started using it, and then I actually, really got into it. And I've been doing it professionally for about 2 years. So now I'm working at prefix.dev, building this guy, which I'll tell you more about in Rust. Like everything is Rust. Most of our stuff is open source, so later on you can check it out and see if you're interested in contributing. So a quick agenda. This talk is going to be about SAT. It's going to have some mathematical notation, but I'll guide you through it, so it's not going to be that hard, I hope. I hope that after this talk you would say like, okay, I think SAT is pretty cool, I think package management is pretty cool, maybe something I want to look into. So I'll tell you about our SAT solver. There was this talk previously about PubRub, which also is kind of like, not really, but like kind of a SAT solver in a sense. And we're doing things a bit differently, but it's very relatable problems and challenges. And some Rust-specific optimizations and patterns I'll get into, and then I'll have a summary. So let's zoom out for a second. So what are we actually building? Well, I think this is pretty cool. So meet this guy. This is Paxton. We call him Paxton. It's our kind of our company mascot, and we use him throughout our different projects. So I'm working on a project called Pixie, which the slogan is package management made easy. And you would think, why do I need another package management tool? Well, it's a bit different than things that are out there. It's based on Conda, which I'll get back into. You see like a small screenshot from when we released, so it changed a bit, but I think that thing looks cool, so that's why it's included. So Pixie is basically something to set up virtual environments, but with all kinds of packages, as you'll see. It could kind of be seen as a local Docker, kind of like, because it builds like a virtual environment, and you can run stuff in it, or multiple environments, and a lot of stuff you can do. And it runs on all major platforms, and it's built in Rust. Like it's full. Most of it is Rust. Or like it's all of it with Rust. So this is the Pixie toml. This is like similar to a Cargo toml that you would use. And it has a dependencies section. That is the thing in the middle. That's the most interesting thing. And that contains all our dependencies. And it can be a lot, and it can be a lot of different things from different programming languages. So that's something that I'll get into. So what is Conda exactly? Just briefly, because people might not know or think when I started with it at Smart Robotics, our previous company, I thought this is a weird Python thing, right? Well, it is a weird Python thing, but it's also more than that. It just manages like cross-platform packages, and basically just, you can install a lot of stuff with it. I'll show you. So this is Conda Forge, which contains a lot of Conda packages. So it has SEO3, for example, or it has Python. You can install Python with it, similar as to UV does it. And you can install GC even. So you can have one project that contains Lua, Fortran, C, Python, and you can describe most of it with a Pixie toml. But now to get into the meat of things, so condas roots are actually Python. So what does that mean? It means that there's a single package per installation, and that's going to be important. So it's different from Cargo in that respect, that it's more like Ruby or Python, because in Rust you can have multiple versions of packages, and in npm you can have a lot of duplication, right? So that's was also in PubRub talk that makes a difference. So say you would have a root requirement, I'll call it, and that has a greeter dependency, which depends on Flask 3, which is a Python web framework. I don't know if you would know it. And you have a breaker. Spoiler, it's going to break things. So, and that has another dependency for Flask between 1 and 3. And then it would say, I cannot do that now, so I can do that. I can cook that up for you, because it's just not going to work. Because I want one package per installation. So, yeah. This whole thing makes package resolutions an MP complete problem, as they say. And when I made this presentation, like there were some people that said, what's MP completeness again? So let me just get into it, because it's pretty important for SAT, and I think this is the thing that makes SAT cool, so just pay attention. So non-polynomial, okay, it has like some technical terms like non-polynomial Turing machine and stuff like that, but you could also explain like I'm 5 is, it's hard to compute, basically. And it's easy to verify. So you can have a thing and a result, and then it will be pretty easy to verify in polynomial time, to be technical, that this is the correct answer, right? So SAT is one of these problems, but even more, if you look at SAT, which is Boolean satisfiability, so I've now finally explained the term, and it was the first problem to be proven to be in MP by Cook-Levin. Independently. So it's basically, in that sense, a benchmark problem. So that is pretty cool, because why do we care about it then? Well, every problem in MP can be reduced to SAT. That's basically what was proven. And to prove a problem A is MP complete, you must reduce A to SAT. And if both of things are true, then the problem is MP complete. And package management is an MP complete problem, so you can reduce it to a SAT problem, and the other way around as well. And that's pretty cool. So you can think of traveling salesman or something else that's in MP, and then you can reduce it to SAT, and then you can solve it. So you can solve a lot of things with SAT, actually. So let's get back to it then. So I said it was cool, and I hope I told you why it was cool. And specifically, let's get back to SAT for package management, right? So this is our project. It's called Resolvo, and it was based on libsolve first, which is like a solver that's used in different packaging ecosystems like RPM, I think Gen 2 as well, and some other things, and was also used in the old Conda stuff, but it was C code and was kind of hard to maintain, and it was hard to get into, so wanted to have something in Rust. And we couldn't use PubRub for various reasons at the time. So we had this guy. I just want to give a shout out if you ever need have some hairy Rust problem and you need to get someone like extremely good to solve it. We had this guy made like the initial version, and then we as Prefix took it over again and made a lot of additions and changes, and expanded the code base, but also made it easier to work with. And I'll get into some of those things, right? So this is the GitHub page. You can see the contributors there. You could be there because we have a lot of stuff you could do. So if you're interested. And one of the things that we were like, that was an inspiration from PubRub basically, is that we wanted to have good error messages as well. So the bottom is like this kind of, I think we copied it from the PubRub example, like this kind of famous error message, and we want to have something nice as well. Like SAT solvers by default mostly say yes or no, as you'll see, and you have to do some extra work to get like these nice error messages, which we did. I will not get into that in this talk, but yeah, feel free to hit me up afterwards and I can tell you a little bit. That's one of the things I didn't touch as much, so I don't know the full details. So SAT and package management then again. So we have this package management problem, right? How are we going to solve it using SAT? So just a brief aside, again, what is SAT? So I already explained it's Boolean satisfiability. Some of you might know what that means, some of you might not. So what can you solve with Boolean satisfiability? We saw that it can solve all things in MP, right? So Sudokus are solved with SAT. Like funny story, my colleague Bas used to write Sudoku solvers for when he was on his break because that was fun. Then he made one when we knew of SAT in SAT, and it was just like it could solve any difficult Sudoku so fast it wasn't fun to work on the solver anymore. So it's pretty effective at that. But they also use it for hardware verification. So you have a CPU and it has like paths, and you need like to know that the paths are correct and that because there are a lot of paths in the chips and which one is fast and the fastest path and stuff like that. So one of the other things it's used for. Okay, so now on to the Boolean equations part. So we have this Boolean equation, and I'll briefly explain what's there. So these things in purple, or the first block, I don't know if the color blindness checks out, but these are variables, right? So the x1, x2, x1, x2 is variables. Then the whole thing on top of it, like in the round brackets, are called clauses. And then for me, always a bit confusing. But if something is negated or not, it's also called a literal. So it can be either a variable that's true or a literal. Yeah, so that one is negated. So those are literal. So if you ever see literal, then it's this thing. So it's a variable with an extra, basically. And then the goal of SAT is to basically solve a set of these equations. So these are in what they call conjunctive normal form. So that's with conjunctions in between. So that's the ands in betweens and the or in between the literals or the variables. So for example, we set a to true, then the first term in that equation cannot be true because it needs to be false. That's why I made it gray. So that's what you'll see in this presentation. Like everything that's green is not true, but it makes the clause true. And then we say the second clause, B is true. So we can conclude that B must be true. So in this case, the whole thing is true. So yeah, that's great. We just solved our first SAT problem. And if you get confused, by me, I got confused a lot by these symbols, the or and the and. But how I tried to remember them, the or is like a guy shrugging, like, or, yeah, it doesn't matter, whatever. And the and is like kind of like, you have a lot of, when I looked at the symbol, there are a lot of animals that are in the shape when they're together. So maybe that's an and. But if you know the or, the shrugging guy, you'll be fine. It's a thing I use the most. So, okay, so we know a bit what SAT is. So how do we encode rules for packaging, and like how do we use Boolean logic for that? Well, every package version is represented as a variable, like the variables you saw before, and package rules become clauses in the SAT solver, right? That's all it is, basically. So let's look at an example. So say you have the SYN crate, yeah, pretty well known, right, in the Rust ecosystem. Say you have these versions, and only these versions, like a SYN, let's say our packaging ecosystem only has versions. You could have pre-releases and things like that make it a bit difficult, but let's just do versions, and then we just map them to variables. In this case, we say S1 to 4, right? I think that's straightforward. So now how do we, for example, SYN, I just checked on crate.io, requires Unicode indent. So, well, cool, we want to encode that. So it's a bit weird, but we say, so either what has to be true is that not SYN is included, so then we don't need Unicode indent, right, if we don't require it anywhere else. Or one version of Unicode indent needs to be included. So if SYN is false, like it's not included, then the whole thing becomes true. Or when SYN is true, then you can't use the first term, so the other terms need to be true. That's how you kind of need to think of it. And anything you want to do, you have to make this like gymnastics to get that into clauses. So let's tie it all together for this require stuff. So we can also have a root clause, which we just say by default has to be true in our solutions. And by making it this root with this true, it's quite interesting, because then we can have top level dependencies. So say we have this cargo toml, and then we have those two dependencies, right? Anyhow and SYN. So we add a root clause, so that's the first part. And then I still want to use a clicker, but that doesn't want to work. And then we add SYN, so it's not root or one of the SYN dependencies, and it's not root and one of the anyhow dependencies. So if all of these are true, then this thing is solvable. So say Synon anyhow did not have any dependencies itself. Like if this thing's, if you could select something that makes this true, then this whole thing is satisfiable, and then you can get like a result. Like you can use the variables that are true, and then you know which ones you selected. Basically, that's how it works. This is all there is. End of presentation. Not really. There's some more stuff. So now let's get into the more interesting things. So as I said, Conda only allows one version per package, right? So as an example, only one version of for package Flask, which we encode as F, is allowed. Well, okay, great. So we have this clause where it's either not F1 or not F2. So if both are false, then the whole thing is false. So either one of those has to be true. But you can't use ORs for this thing, like you can't concatenate it into ORs. And it was also in the PubRep presentation that this is the one that makes the SAT clauses explode. But you have to add them for all, like you have to kind of do a Cartesian join between the things. So it's, so you have a lot of clauses here. But most SAT solvers are pretty good at clauses and solving those. But it's still like this one explodes a bit, so it's ON quadratic, or it's technically n choose 2, I think. But but in the end, asymptotically, it becomes quadratic. So there's something we have to think about. So all other packaging rules, anything that you can think of, like I always want versions higher than 6 or whatever you can think of, you could if you can reduce that to like a SAT problem, then you can solve it. So the idea is we encode a rule, think of anything, then we fit this into a SAT clause to make it into a solvable problem. And then we add those to the equations, then we run SAT on the thing, and then we profit, right? It's done. So yeah, that's it. That's how you make your own solver. So let's look at the SAT algorithms now, and there are 2 of them are on the bottom right, which I took from that page where it's solving a Sudoku. I'll get into what each of them was. So you could think of SAT as a depth first search, right? You could just go brute force your way through the equations. That works, but is slow. Then there was this algorithm called Davis, Putnam, Longman, Loveland. So there were 4 guys, and they made it in 1961 already. So if they've been researching this stuff for a long time, which is kind of nice because that's why we can use all that research. And then somehow weirdly, this is like, people say this was introduced around 1996. I don't know why it's around, but it's sometimes 1990, a bit earlier, a bit later. There's also briefly in PubRep talk, and this is called conflict-driven clause learning, CDCL. And you can already see on the left that the number of assignments just like racks up. And if I would let this run on that website, then CDCL is much faster to complete. So there's even like you have pre-CDCL solvers and post CDCL solvers are basically what most people are using. I think the biggest SAT competition still kind of use some variant of a CDCL solver. So it's like that. So one of those pivotal algorithms, right, that change things. I'm going to give like a high overview of SAT, and it's going to go pretty quickly because I only have 35 minutes. But I hope I make it a little bit understandable, because I thought it would be really cool if I could explain the algorithm to you briefly. So step 1 is make a decision. So say you have this clause, and you set A to true. Okay, you might already be seeing where I'm going with this. So we use unit propagation, and sometimes it's called Boolean context propagation, which is also a nice word, but I use unit propagation because I learned of that one first. So what happens now, so we set A to true, so we already seen some of this, right? So the A term becomes gray, so it cannot make the clause true, and then B, we must conclude that B must be true, right? If we want this thing to be satisfiable. So that's basically what the SAT solver kind of does. It makes a decision and it propagates it. And the unit thing we'll come back to a bit more, why it's called unit. But basically a unit, if it like reduces to one term, you can infer what that is. So that's the unit that you take out of it. And then this is the thing that sets CDCLs apart. That is going to be conflict detection and backtracking. And I'll get to it both. So I made this system of equations, which is contrived, but works like how I wanted to. So we have C1, C2, C3, C4, and all of these need to be true. That's our goal. Let's see if we can do that. And then we set the decision level, and that's a bit interesting because that's will give us the amount that we want to backtrack. And then we set A to true. So that's the first decision that we'll make, and it's not a good one, as you'll see. So we set the decision level to 1 and A to true. Okay, so we couldn't do anything with A. We couldn't propagate it because it's nowhere else in the equation. So let's make another decision and set B to true, right? Okay, well, let's look at clause 1, and that doesn't fulfill anything. So we now know that C must be true, right? That's what we conclude. And then it waterfalls, and I deliberately put this all in one go because that's normally what you see happening in the SAT solver. Like a lot of happens in one go. So now we can start propagating. So C is now, now B is true in decision level 2, and then we must conclude that C is true. So then from clause 2 we can conclude again that D must be true, otherwise the equation does not hold. And C3, then E must be true, and then we get to C4. And then we want to say, yeah, E must be true, I think, but it's not, because C4 is a unit clause and it says, yeah, E must be false. So but E cannot be false, so it's a contradiction, right? So that's what happens with a SAT solver, we have a contradiction. So how do we try to solve this? So we make this something called an implication graph. You can forget the name, but basically you make a graph up until the decisions, and the nodes are the terms, and then the edges are the clauses, and you kind of we're going to walk back over this conflict graph and then see if we can get a new clause that we can learn from this. That's the goal. So we are at the bottom, and then E was true right there. But now we want E to be false because we use the opposite of it. And then we kind of like, this is not the totally correct explanation, but bear with me. We kind of plug that in back into C3. And then, yeah, so we must conclude from that D must be false. And we plug that one back into C2. And then we must conclude that C must be false. And then we plug that back one into C5. And then we stop, because there's an important rule here where we stop backtracking not to make things confusing, we stop going upwards because we want to stop when we're at a clause where only one literal was decided in this decision level, which was decision level 2, and that is literal B. Okay, so we stop. And then we learn this clause. So A, not A or B. Then we go back and we backtrack. And we have to backtrack back to level 1 because level 2 was just not working for us. So go back to level 1, and then the cool thing is now we can add that just a clause because it's a new clause that we learned. It's more information. And then we make a decision again. So now we have to make this following decision because A is true, and we have this clause where we know that B must be false. To make this whole thing true, then B must be false. And then we plug that into C1, and it kind of propagates downwards. So B must be false, C must be false, D must be false, and E must be false, which is good and is satisfiable. That's basically what it does, but then it does it on a really large system of equations. So now I did this with an abstract problem, but this will normally be one of those clauses that we encoded before and that we want to backtrack, and we want to find packages. And this can go on a long time, especially if you don't constrain package versions, as we'll see. So now some specific optimizations and patterns that we had included. So there's a number of SAT optimizations that you can do, and I'll only explain one, but there are loads. But there's also some Rust things that we kind of did in Resolvo that I think were maybe a little bit more appropriate. Because the SAT ones are more general, right? But let me show you what we need to optimize for, right? Because, so say we have this Pixie TOML, which is just something that defines a workspace and Python as a dependency. So what does this give us in statistics? Well, you see it's pretty small, so there's not a lot of clauses in there. it's it's going to be easy to manage for the SAT solver. So this is okay. So this is a toml that's being used in the SciPy repository. I just took it, and then I took some statistics from it, and here you can already see like the total number of variables racks up, and the total number of clauses especially becomes big. And we already did a huge optimization here that I'll get into in the next slide. But then it's already becomes a bit more difficult for the SAT solver, although this one is, I think, takes like a second or two. And also to show you that package management can be a bit fickle, PyArrow has a lot of versions, and this one just had a lot of more stuff going on, right? But I just add PyArrow now, and now bam, I get more than 1 million clauses, and it takes on 36 megabytes of memory, which is a lot. It's just like Boolean things, right? So I told you about those forbidding same package versions clauses, and that one especially gets bad, but we did an optimization here called binary encoding, a SAT thing again, which this was what it was like before. So it was like a gigabyte of clauses and just so much more. And the binary encoding just fixed a big part of that problem. So I mean, so sometimes they say you shouldn't like these big O things don't matter. Well, in SAT they do, because you really have to keep the number of clauses down. So one of the specific optimizations, which is kind of simple, like a clause is a database, right? So what do you do with a database? Normally you index it in some ways. And we can use the following like observation of it. So remember when I said unit, like a unit clause? So we only care about the clause when there's 2 variables left, because if one of them is set to false, then we can make a conclusion about the other thing. That's very strong in SAT, right? You want to make them like the biggest amount of conclusions possible, because it just makes it easier to solve your problem. So S must be false. That's basically what this says, because it's unit. So what we do is we just index 2 literals that you have to choose kind of intelligently. And then when a literal is set, then we just move that. And now there's 2, so now this becomes an interesting clause. But that way we only need to propagate those literals that we're watching. And because it doesn't really matter which one goes first, like in the end, it has to all like kind of like collapse. But it only happens when you have like these 2 variables left. So another more Rusty specific optimization that we do is like we use, we want really fast lookups, right? Because we have really a lot of clauses, and we could use hash maps, but it's a bit slow. So we use something called arenas, and there's also a Rust crate typed arena that Rust Analyzer, for example, uses, that you could also use if you want something like this, but we had some specific things that we want to do. And it's basically a chunked vector where we just do an index to a specific value, and it like you can only add data basically, and a mapping, and you cannot unset it. Like once it's in the arena, it's there. And with a mapping, it's the same thing, but then it's an optional value basically. So mapping is, so arena is kind of like something that gives you an ID for a specific value, and then the mapping is more of like like a hash map basically, and then you can set that whole thing to none. So this is what it looks like, and what do we use it for? So we use it to look up for literal to clause, for example, or a package name to like the package data and stuff like that. And as I said, we have to do a lot of lookups. Like if you propagate, you have to look at a lot of clauses. Like this kind of adds up. It's like most things that we took that from libsolve, and I think most SAT solvers use something like this. It also enables something that's called the niche optimization. I always thought it was a niche because it isn't used much, but I think it's because it optimizes into the niches of things. You'll see that. So we have like an option, non-zero U32, which is the same as non-zero U32. So first our clause ID was just a U32, or no, but now we can use like a non-zero U32, and that's like a pretty neat optimization, because an option is normally like a value value and a discriminant, right, that says which thing it's pointing to. But because you know that the non-zero U32 cannot become 0, which is kind of in the name, we can use 0 for the optional value. That's cool, I think. So we add the mapping again, which I showed you, and that has an option of clause, literal to clausity in this case, and that saved us 50% of memory. So that's just easy to do and might be useful, I know. We support multiple packaging ecosystems. And how we do that is we took inspiration from PubGroup here by making some kind of traits that you can implement, and then you should be able to support a new packaging ecosystem. So we have different implementations for Conda, PyPI, but we're not using this anymore, but we do have it. There's one for an unstable one for RPM, and there is one for Debian, and yeah, maybe yours, I know. And our assumption is that with these things and how we set it up, like we might need more clauses, but we can basically support any packaging ecosystem that we want. So how we did that is we have two things. So it's basically, let me just, do I have a pointer here as well? Yes, we have an interner, which is this thing, and we have a dependency provider. And these two traits, the interner, it's maybe a bad name, but it's kind of like, you saw those things with the arenas, right? You could intern data, and this, yeah, you can query information about that here. And then the dependency provider is just like these functions you need to implement in some way, and then that's all you need. The software can kind of use that to get the dependencies that it needs. So yeah, we have something in the test called bundlebox, and it's a requirement. It's a very simple packaging system where there's just a package, which is a requirement, and it has a package that can have one integer as a version, and you can say I want 0 to 2. So we basically made the implementation there in the tests, and then you can just add it to a test. So we have this provider, and we provided some packages, and then we say the requirement is RustNL, which requires this bar 0 to 7, sorry. And then we make a solver and make a problem, which is also a Resolvo thing that has requirements, and then you solve it. And then you get this. So then it's solved. Oh, I need bar with version this, and I need RustNL with version this. Like, this is a simple problem, but yeah, we use it in test, for example, which I think is nice. So yeah, we try to really do our best to expose something simple. Something else that's interesting is that we have an async and sync code path. So solving is like computational heavy, right? So we don't want it to be async per se, but there are multiple ways of getting your dependency. So either it can be upfront, which can be like a package database, or incremental, like you have to go to one site, or you have to download the wheel, maybe even in Python or something to get your package, which is like incrementally built up. You don't want to do it all up front because it's going to be slow. So we want to keep the sync path for Conda, because that does have it up front. And then we wanted the incremental path for PyPI in that case, but also other packaging ecosystems. So combining sync and async in one code base is difficult, I guess. There are like multiple ways to do it, and how we did it was that our internal functions are async, but they're not dependent on Tokyo per se or a runtime. But we can force like a sync call. And how we do that is we have the sync world and the async world, right? So the sync world is the solve. This is sync, but getting stuff is async, because it could maybe hit the network or things like that. And you need to marry these two worlds. So yeah, want to marry them. So we have the dependency provider that can provide a runtime for the solver, and that uses like an encoder to block on. So we have this is in the solver, so it at some point says like, okay, I want to encode some new values, so get some new packaging data. And then, how do I do that? And how do I make that sync or async? Well, we had a pretty simple solution in the end. So we have one trait, the async runtime, where it's a block on function, which for Tokyo does just a Tokyo block on. So it does like what you know in Tokyo. It runs the block on where it's, where it kind of like blocks on that thing and spawns it somewhere and waits for the result. And then we are using the now or never runtime, which has a function called now or never. So even this is a function that if you call it, and this is not dependent on Tokyo, but it expects the future to instantly resolve. So in essence, making it a blocking call again. So again, we have that async runtime, that block on, so it either calls this one or this one. So you need Tokyo for this and you don't need it for this. So that's how we kind of like split that, which is not like something that everyone can use, but I thought was pretty like a fun thing because we kind of like stumbled into it. So I thought it would be kind of cool to share. So yeah, we're all open source. And yeah, really thank you for listening to this. I had a little time, had to go through a lot, so hopefully I wasn't too fast. But we have 3 projects. So it's Resolvo, that's the solver, and yeah, it's open to contributions. We have Rattler, which is like our underlying library to all things Conda related. We can use a lot of help there. And we have Pixie, which yeah, if you're interested, you can check it out. For Rust developers, we use it, for example, to run our Rust project and run TypeScript and manage like multiple programming environments and things in one. So we can do basically a Pixie run front end, and we get like the back end and the front end that starts up. And yeah, so you can do some. It might be useful as a Rust programmer, but it's especially useful if you combine multiple programming languages. So that was my whirlwind tour, and thank you for listening.
Cool. I think we have a couple minutes for questions.
Thank you for the talk. First of all, one small comment is that MP doesn't stand for non-polynomial, but that's just my pet peeve.
Oh, really?
It's non-deterministic polynomial time.
Okay. Thank you for correcting me.
But my question is, why did you choose to make a SAT solver, not a constraint solver?
Like
Because it
answer set
seems-
constraints, or?
Like with constraint programming.
Yeah, so we basically, I don't know if I have a super correct answer for it, but Conda was using libsolve, which was a set solver. And then we didn't know a lot about it, so there might be also different ways around it. Yeah, so we basically based it on that, and we know it works well for that ecosystem. So that's why we went with it again, and we were sure we want to have like one-on-one results for having the same input, having the same solve as an output. So yeah, it's maybe ignorance, but also just those things, right? That's
All right, thanks.